All right, cool. How's everyone doing?
Otherwise, on the lesson, not too good. Still stuck with RNNs. So, I find the RNN part a little difficult to understand the way Jeremy explains it. There are much simpler explanations elsewhere, I guess. So.
Well, let's jump in and kind of work through that. How far have folks gotten? Did everyone get through the whole lesson 6?
I did the first half.
Okay.
First half.
First half was kind of more of a review of or continuation of the movie lens stuff. The second half is more the RNN stuff. I did more the second half. The movie lesson didn't really do much for me, so I kind of blew off the first half of lesson 6. Cool. So, do we want to start off with you, Kai? You're going to talk about the Jacobian Hessian stuff.
Yes, I can do that.
Awesome.
Okay.
Hey, good morning, everyone. It's Chuck, and I'm on the phone, so I can't see all your screens this week. Just thought I'd give you a heads up if you want to explain a little more of your screen. I'm going mute now. Later.
Okay. Hi, Chuck.
Okay, so
I made a little harder than usual.
Yeah. I hope you can follow, but I'll try my best. Okay, share the screen. So can you see my screen?
Yes.
Yes.
Okay. So again, I have just some handwritten notes. I think this one is the first. Yeah. I really made these notes in the last 15-20 minutes. So if anyone finds an error in my calculus, please just interrupt me. I'm going to start with this one. Yeah. So first, to just remind most of you of types of functions there are. So I think most of you will at least know this one, this is just the parabola. It's a scalar function with one variable. And you can also have a scalar function. So scalar means it's just outputting one value. You can have also scalar functions with multivariable. So x, y, and z, for example, that's the typical 3 coordinates in the room thing maybe know from school. And then you can also have a vector as output. So this is basically composed of 3 functions here. And it's also multivariable. So that's just basic calculus. And then to start off, just also to remind you, this is the derivative of a scalar function. In this case, it's just the parabola, which you can see here. And the derivative in this case is 2x. And it really just describes the steepness in the function here. So here it's very steep in the negative direction, and so it's a higher negative value, and here it's steep in the positive direction, and so it's here in the higher positive numbers, and here is the steepness is 0, so it's basically flat at this point, and you have a 0 here. So this here is a notation how to write this. This just means please build the derivative of function f into the direction of x. So in this case, there's only x. You can't build a derivative in a different direction than x. Maybe some of you know this in other notations like this here or this, but it's the same. So it really just means build the derivative of this function into the direction of x. So then I have point 2 on another sheet. So this is 2. So this was how to build the derivative of a scalar function with one variable, and then a derivative of a multivariable but scalar function. So a function where you have x, y, and z. You can basically build 3 partial derivatives here. So you take the function and build the derivative in each direction, x, y, and z in this case. And so when you build the derivative into the direction of x, you basically consider all the other variables as constants, like if they were just numbers. And so that's a way to describe all three derivatives of this function. And then the next step would be to build the derivative of a vector-valued multivariable function. And so this is the function which is made up of three single functions. And there you can build three derivatives, so one derivative in each direction for each of the functions. And you can arrange those derivatives in such a matrix. And it's really just a way to organize this derivatives you have here. So for example, this one is function 2, which is this one here. And you build the derivative into the direction of y. So in this case, there is no y in this equation, so it's 0, because all the other values are considered constant. And when you build the derivative of a constant, it's 0. And yeah, so that's a Jacobian matrix. No rocket science here. Okay, that's 3. Yeah, and then you can also build a Hessian matrix, and this is a way to arrange the second order derivatives. So when you have function like this here, for example, you can also derive this function again. And this tells you how the change in the change happens. And when you build the derivative of this function, for example, it's just 2. So it would be a straight line on the y-axis of 2. And when you do this for a multivariable but scalar function, you will get this matrix here. So it's the second order derivative you first derive into direction of x, and then again into direction of x, or into direction of x, and then the resulting equation into the direction of y. And that's what you end up with. So this is, I think, this function here. No, wait. Oh, yeah, it's here. So if you derive this function here into x, you get this, and when you derive it again into the direction of x, you will get this. Okay, so is that somehow clear?
I feel like if he had just said the matrix of first order partial derivatives and the matrix of second order partial derivatives, it would have been a lot clearer.
Okay, yeah, okay. But it's
meaning when he referenced that in the course, like I don't recall him. I recall him saying that the Jacobian was related to the derivative, but he mentioned the Hessian. He didn't say it was just the second order derivatives. It makes total sense.
Okay, yeah. So, but this is just a multivariable function. So for neural networks, we have not just multivariables. So the variables in the function of neural networks are the weights. And we also have a vector-based function because you don't put just one number into it, but a vector of numbers. And so you have to build a Hessian matrix of a vector-based, so on a vector-valued multivariable function. And that is a tensor, because you can, for each of the equations in the Jacobian matrix, you can derive it into all the directions you have. So you get a really big tensor when you do that. You get one more dimension for the second order derivatives, yeah. And that's like this here. So you build the Hessian matrix of the first function, and then the Hessian matrix of the second function, and the Hessian matrix of the third, and you have a tensor of order 3.
Which is really it's the MNES data set. You can use some kind of like a neural net.
Sorry, I did not understand that.
Yeah, whoever that is was breaking up.
Sorry, I'll jump in then. So the Hessian, you clearly are assigning a column for x for each essentially direction that you are creating the second order derivative for. How does this work with even a higher dimensional? The Hessian is always a 2D matrix, correct? It's not an n dimensional matrix.
Yes. So when you have more dimensions, so this is just really x, y, z. It's the examples you maybe know from school. If you have a big function like in a neural network with millions of weights, maybe you have a million dimensions, and you would just get a square matrix that is much bigger, but it's always squared.
Very good.
Can you go back to the next one with the vector representation?
Yeah.
Okay.
So you basically just build one Hessian matrix for each of the functions you have in your vector value function, and yeah, stack them together like in a tensor. Actually, I did not look into how this is actually used in the computations for neural networks. I mean, Jacobian matrix basically describes the steepness of the direction you want to go in, and the Hessian matrix is, I think, for how strong you want to go into a direction, because you are looking on how fast the gradient is changing in the second order derivatives. And I know that it's computationally infeasible to to symbolically create all the Hessian matrices for this neural network. So they're using tricks to optimize this. So it's, again, like in a lot of other parts for neural networks, it's pretty simple math when you do it on a small scale, but when you scale it up to this big networks they use in deep learning, they use a lot of tricks on how to optimize these computations.
Right. And those tricks tend to be around the same trick that's used in Fourier transforms, which is to basically do partial calculations early, store those, and then use them in later calculations. So that's just one insider game. That's very typical to essentially try and reuse any calculation that you've done in the past in order to make things go faster in the future.
Good.
Okay, that's all from my side.
So there is no, sorry, I'm going to come back to the Hessian again.
Sure.
Is there any known, does anyone know of an application of the Hessian, which is actually, I understand conceptually, I have a physics background, so I understand second order derivatives from an intuition point of view, but in terms of application, it's really just used for tuning the rates in like learning rates, things like that. Is that what it's actually used for?
I think it's used to determine how much you want to go into the direction to change the weights. I think it's used in this part of the neural network training. So you have to decide how big the step is you want to take.
Mm-hmm.
And in this, because it's describing the steepness of the gradient.
Mm.
Mm-hmm.
Very interesting.
Sorry, one question. It would be related to the momentum that Jeremy was talking about?
Yeah, probably. I actually did not look into how, this is really just from my mind, I have from my engineering background.
Okay.
So
okay.
I did not look into how it is used in neural networks, but maybe I can do a follow-up next time.
Perfect. Perfect, thank you.
Okay. I'm happy to jump in.
Pulled up on I was trying to look for some answers to this one, and there's a note here in Quora. I don't know how reliable it is. It says, in deep networks, the Hessian is far too large to actually compute, so things like K-FAC and quasi-Newton methods are needed.
Yeah, okay.
Which I've heard of before.
Well, Newton method is really, I think it's just, it's not, you are not building a symbolic differentiation of these functions, but you approximate it with a numerical method at the point where you wanna calculate it.
So something like a finite difference or something very simple.
Yeah.
Mm. Interesting.
Yeah, I mean, you can imagine how it's getting really, really big if you build all this Hessian matrices.
one benefit is that it seems to be linear in that you don't have lots of branching in there, so you could scale it on a GPU. So it's plausible that you could actually calculate. I guess it's symbolic though. I don't know. I'm just. Does anyone know if the Hessian and the Jacobian can be scaled out on the GPU, or is this something that's very much a CPU because it's symbolic? I really don't have an intuition on that.
I don't know.
No, that's okay.
The differentiation is done on the GPU, I think. That's what PyTorch is basically doing, right? So you
numerically, yes.
Yeah.
So that's a numerical differentiation. This looks symbolic to me. Sorry.
Well, I think it is symbolic. So you are calculating when you're using the gradient, you are using this symbolic differentiation and then crunch the numbers.
Well, I don't think. I think you only have symbolic differentiation if you know. I mean, in his toy examples of a linear function, if you know the symbolic formula of that linear function, but in almost all cases, you don't have a formula for, what the output should be. So I think in almost all cases, it's numeric, not symbolic.
Yeah, but I think in this case, so when you these operations with weighted sums and the weights, that's very easy differentiable. And it's, I think, the really big step in faster computations is done by using the symbolic differentiation of the network to crunch the numbers, and not doing the numeric where you have to go stepwise and do. So when you do something like Newton, for example, you have to do multiple steps to get the gradient. And in this case, for the neural networks, you have to use a differentiable activation function, and you are using the weighted sum, and you can differentiate the whole thing. That's basically what he's doing by using the chain rule. That's symbolic differentiation. So you're not building for the whole network. You're not numerically differentiated. You're using the chain rule to build this big multiplication of matrices.
I think when you're differentiating these things, you're differentiating the loss function, and the loss function is really, the error between your expected value, which is almost something you never have. So that cannot be symbolic.
Well, you want to really look at the partial differentiations for each weight to tell how much you have to change the weight to go into the direction of the optimum.
I think the confusion is around the fact that the weight itself, the differentiation is only happening on the coefficients. We're not really doing data sampling. The assumption is that the weight function itself is linear or known. So that's the approximation is that the weight is a linear function or something like that. I don't know whether it's actually a linear function, but you essentially make an assumption at the beginning about the weight, the formulation of the weight function, and then you essentially do the symbolic differentiation on the coefficients is how I would badly try to explain it. Yes.
Meaning, so the loss function that you're trying to approximate is, not linear, but the weights you're assuming are linear, and you're using when you're optimizing for the weights, you're using symbolic differentiation in that loop.
That's my guess. I don't have any evidence for that, but that intuitively seems to be the case. Because otherwise it wouldn't be symbolic at all. You have to have a notion of what the functions is that you're adding the coefficients for. Otherwise, it's just a bunch of numbers. So,
what I understood is that a forward pass through the network is basically you put in data, and it's a function of a function of a function of a function that you pass through the network. And then, so it's you use the chain rule to differentiate this big function, And in this function, the weights are the variables. So it's not x, y, z, but all the weights. And you want to have the derivative of this network function to find the optimum. You need the steepness of this function for each weight to find out how much you have to change it to correct for the error. And I think the loss function is in this consideration not important. So this whole autograd thing from PyTorch is really just building this big differentiation of the function which the neural network is.
Mm-hmm.
That's what I understood.
Well, I think in the forward pass, I mean, there is no loss function involved. I mean, it's only the loss function is involved only in the backward pass.
Yes, but you need to have the possibility to calculate the derivative of the function, and the function is the neural network. And you don't do that by differentiating it numerically, but you have this symbolic differentiation of your network to calculate this.
Is there an example in one of the previous notebooks that does this? Can anyone remember one?
The place to look for it would be in the spreadsheets, because they're so unwound that it should actually be, you should be able to look into the spreadsheet and actually see this. But I think that's hidden away.
So, I mean, I'm kind of with you, Sebastian, in the sense of this doesn't necessarily align with my intuition for how this thing is working, but I don't know that I could articulate at all. But
I think David's right. It is in the spreadsheet, and in the spreadsheet, he uses a toy example where you actually have, you know what you're supposed to have, which is a linear function. You know, y equals ax plus b is in the spreadsheet. So, you never have that example in real life. I mean, you know, the spreadsheet was just a teaching example. It's a teaching toy example.
If we assume that that we're doing this kind of linear differentiation using the chain rule, linear symbolic differentiation using the chain rule, like would that also imply that each of, like, some structure about each of the layers, like if the first layer's weights, or if one layer's weights are linear, then the layer beyond that weights are, you know, parabolic or something like that, and the layer beyond that weights are cubic or something?
I don't think so. I think it's always linear. The weights are, you know, the weights, you compute the activation with the linear function of a weight before ReLU.
I guess what I was hearing, and I may have totally misinterpreted this, was that is there some, or is what you're saying, Kai, about the application of the chain rule is that each of the layers represents the application of the chain rule?
So I think each of the layers is one function in the chain of functions, and you have to use the chain rule, and what basically comes out is a multiplication of multiple matrices.
Right. So, but does that mean that if each layer is one of the functions in the chain, does that mean that layer, you know, n plus 1 is layer n is the derivative of layer n plus 1, and so on through all of your layers? Is that what you're trying to say? Or am I just totally...
Can you repeat that?
Yeah, Sam, basically when you do back propagation, right?
Mm-hmm.
Let's say if you have 3 layers, So, you know, and your loss function is getting adjusted at the end, and let's say you need to change the weights. So you will go backwards from let's say your last layer to layer -1. Now that is one you know, that is where the first derivative change takes place. You know what Kai was saying, df by dx and df by dz. When you go to the second layer, the second layer's differentiation as per the chain rule will multiply with the last layer's differentiation. So it is chain rule is multiplication of the derivatives at each of the layers.
Yeah.
What I have understood, right?
Yeah.
Yes.
Yeah.
And on this question of, you know, where is the Hessian matrix being used, I came across a couple of Quora articles. I think what one of them says is that, you know, when we do simple calculus, you know, the second derivative helps you find out the minimum and the maximum points when you only have two variables. But once you start getting into, you know, thousands of variables, then you need essentially Hessian matrix to help you you know, find these minima and maxima, and it also makes a reference to something called the saddle point, you know, which is a very famous concept in machine learning. So he says that Hessian is used to find the extreme values of functions of more than one variable. This is the Quora article. I'll post a link on the chat.
So I also found a blog post, and it says that, so in order to minimize the function, so the neural network, one obvious approach is to use steepest descent. Start with random values for the parameter to be estimated, find the direction in which the function decreases most quickly, step a small amount in that direction and repeat until close enough. That's basically numerically what numerical differentiation does. But we have two problems. We have an algorithm or a computer program that calculates the nonlinear function rather than the function itself. The function has very large number of parameters, hundreds if not thousands. One thing we could try is bumping each parameter by a small amount to get partial derivatives numerically, but this would mean evaluating our function many times, and moreover we could easily get numerical errors as a result of the floating point arithmetic. As an alternative, we could turn our algorithm or computer program into a function more recognizable as a mathematical function, and then compute the differential itself as a function either by hand or by using a symbolic differentiation package. So I think the you need for this optimization process, you need to have the derivatives of the complete network, and you don't do that numerically. You do this part symbolically. And it's pretty easy because it's just the chain rule applied to a bunch of layers and activation functions. So you basically get a large number of matrix multiplications, and that's what graphic cards are excellent for, and that's why it's so fast. And on graphic cards, you even do it in batches, like so you are multiplying tensors and not only matrices. But I can do a follow-up next week, so maybe I can try to dig a little deeper into that, and we can continue the discussion next week.
Yeah, no, I think I'm getting somewhat of a little bit of intuition based on listening to this. So essentially, when you have your function, it's assumed to be some multiplier of a variable that's to some power. And so if you know, if it's some, if it's x to some power p and there's some linear scalar at the front, then essentially you can do symbolic differentiation because it's just a very simple function. So in that sense, I think that's my intuition anyway, is that because it literally is, multiplier times some variable to some power plus some other multiplier by some other variable to some power and so on, you do actually know the structure of the equation. So you can actually do the symbolic differentiation.
So when you really look at the functions in this chain of functions, it's just multiplication because weights times the vector that comes in, and then the sum, and the value is I mean, it's basically a linear function. It's just nonlinear because there is a step in this function. And so those are really, really, really easy to symbolically differentiate. And it's more optimal to do it like that.
Cool. Very interesting.
Thanks, Kai.
Yeah, very good, Kai. No.
Sure.
Absolutely. Thank you. One,
I have a small piece on the ResNet stuff as well when you're ready.
oh, awesome. I just shared my screen. I, just kind of surveying, looking for possible explanations of this. I came across this paper, which looks interesting. At the risk of introducing a totally different term, so not numerical differentiation or not symbolic differentiation, this paper is looking at what they call automatic differentiation, which is distinct from those two. And they kind of argue that, the folks that know numerical differentiation don't really know about automatic and vice versa. And there are some interesting kind of examples and visuals about how the forward pass and back prop work. And then they have some kind of pseudocode examples in here. Obviously haven't read it in the 30 seconds since I pulled it up, but it looks like it could be interesting for getting some additional intuition in this.
Great. Can you post the link?
Yep, I will. I just dropped it in the Zoom chat and I'll put it in these notes as well. All right, cool. David?
Sure. I'll just grab the screen if I may. Are you seeing this?
Yes.
Great. I'll hit the little button down here in the corner. This is a 4-slide deck, so don't get too excited. This is the main principle behind. So I'm talking about ResNets and ResNext. So a ResNet, it stands for a residual network. This is specifically related to, as I understand it, convolutional neural networks. And in around 2014, this basically won all of the competitions for the various different data sets like ImageNet and CFAR and COCO and all the other really cool data sets that are used for testing image recognition algorithms. So essentially, the intuition that I have gained is that the deeper the network, the better it is at recognizing high-level features. So here you can see, I've tried to draw it out. So this yellow curve here, so you have some function y equals f of x, which is represented by the dark blue line, and you can see it there, it's wiggling away. And then when you try and approximate that with a very simple neural network with just a few layers, you get a rough approximation, which would be the orange line. And then as you add more layers, the intuition is that you will eventually end up with something that essentially very, very accurately replicates the function that you're trying to approximate. Sadly, in reality, this isn't the case. So there's this intuitive understanding that that is what should be. However, in reality, it doesn't pan out that way. And so what actually happens is that there's several problems. One of the problems that you end up with is the vanishing exploding gradients. And my understanding is, and what I've read in the paper, was that this is alleviated by batch normalization. So normalization essentially pulls up the vanishing gradients and pulls down the exploding gradients to some known bound, and then as this slowly starts to expand, it starts to explode and collapse. After a while, after you've done a batch, you then renormalize and renormalize and renormalize. And this is covered extensively in Jeremy's talks. There is another very counterintuitive finding, is that as the networks gets deeper, this is a quote from their paper, So the accuracy gets saturated and then actually degrades. And what these graphs are showing is that the accuracy of a 20-layer network actually improves beyond that of a 56-layer network. Now, these are just conventional CNNs. So these are CNNs that are just exactly what you see in all of the textbook stuff, where they're essentially considering it 2D. The fact that the weights aren't just related in a single dimension, that they're actually related in 2 dimensions. So the pragmatic evidence is that 2 things happen. You reach accuracy saturation, and the other thing is you also hit a kind of a computational inflection point where it just becomes, computationally impossible to actually get these things to converge with more layers. And so the trick that they did was that they essentially, if you look at this picture, so imagine, if you will, that you had a 1,000-layer neural network, but the last 999, the last 99% of the layers actually were just the identity function. This would actually yield the same result as the 3-layer network, because all the additional layers aren't actually having any effect on the activations as you progress through the layers. And this is the fundamental assumption of ResNets, which is, if we start with the assumption that all of the higher order layers are the identity matrix, they're unity, they have no impact on the weights, then there's no penalty for having the extra layers. And so all we need to do is to work out a way of essentially having a small difference at these higher layers if it's adding value, which they're calling the residual. And then this residual then can essentially represent the same as the conventional neural network, but it's very close to 0 initially, and then will only grow if there is a benefit in doing so. So I'm just trying to share the intuition with you. So the pragmatic result is this just kicks ass. It's so much more accurate and can support so many more layers than any other system that's out there, that they can't even compare the results of the higher layer functions to conventional networks because they can't get them to converge. So there is a bit of a leap of faith in ResNets, because it is an intuition that they have tested, and then the testing has revealed this kind of difference between conventional and their ideas. But if we somehow get 10 orders of magnitude more computation, it may actually be proven to be something else. So this is not a theory that is proven. This was an intuition that was tried and had a very, very positive result. Like, it really did have a very positive result. And so this line that's going around the edge there, that's just literally the unity, the identity matrix. So information from an earlier layer is just fed forward directly into higher layers. And then you add this little residual onto that to get to the higher order layers in the neural network. So my intuition
in this case, is X the input, or is this meant to represent at any point in the network?
So these things are stacked up to 50 deep. This cell here is actually stacked. I can show you the paper. Yeah, so X just means the identity. So X is the input, sorry. But if you multiply X by the identity, you just end up with X.
X, right.
Yeah. So f of X, which is this thing between that. So they reformulate. So as Kai was saying a few moments ago, the output of a neural network is the function of a 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 function and so on. And what they're saying is, it is the slight reformulation of that is that it is the function plus X. All right, but the function now essentially is the difference, the residual between X and the next layer, the next function in the layer. I'm not describing it very well. The paper is actually very readable, so if I'm not making much sense, I really do recommend just taking a quick spin through the paper. It's not heavy math. It's actually quite digestible.
So I now understand what you meant last week. So it's actually, so it's really I had this residual thing in mind where these residuals are passed through the network to bypass layers, and that's basically what the identity does, because it's the operator you multiplied with, right? So it's just passing through. Basically, to get a better understanding, you can just think of passing through the residuals and bypass some of the layers, right? Yeah. Okay, that makes sense. And it also makes sense that you can add as many of these operations as you want as kind of ghost layers and make the network as deep as you want to.
Right.
Yeah. Interesting.
And they won the competitions by operating their systems at layers of 150, which is just totally impossible. I mean, VGGNet, which was the previous winner, it's 41 layers.
Yeah.
So yeah, as I say, they don't make strong theoretical claims. They don't. They just say, we have this intuition, we tried it, and boy, did it work well. Which I think was very humble of them to do that. But they're not really pushing it too far. So the one I'm almost done here, by the way. The one thing I did want to share with you, which I think is very timely, is that ResNext is just embeddings. It's exactly the same as ResNet, but instead of having one cell that's calculating a residual, you have n. Just like an embedding, you create multiple different vectors so that essentially you get even higher levels of accuracy because you increase the dimensionality of each of the layers of the CNN. And this makes intuitive sense to me, at least, in my understanding of embeddings. So yeah, when you combine embeddings with this idea of arbitrarily deep networks, you get competition winners. It's just that simple. So embeddings, I can't overestimate the power of embeddings. There's such a powerful idea that you can take one thing that you think is a singular thing and break it down into a bunch of different dimensions, and then have a much better representation of the thing that you're trying to represent. It's very, very profound. So the whole embeddings thing, I think, is one of the critical takeaways I've gotten from the Fast.ai course. I haven't seen that before.
Yeah.
So I'm happy to answer any questions on this. I really was just trying to clarify. I wasn't trying to go into extraordinary detail here or anything.
David, I have a question. The identity, is that analogous? Is that supposed to be some sort of weight matrix, identity weight matrix, or what is that identity?
So the identity matrix is just a diagonal matrix of ones with everything else being zero.
Is that serving as a weight between one layer to the next?
Yes. Yes.
So each layer that has this identity matrix, they have the exact same number of neurons.
Yes.
Okay.
I'll share a different picture with you. So I'm just going to switch to a different thing here. Just one sec. I'll bring up the paper. Where is the paper? Yeah, well, you carry on. I'm just hunting through 1,000 pages here. Just one sec. Here we go. Yeah.
Thought I had the paper nearby too, but it's taking longer to find it.
Coming. The PDF up now, and here we go. Yeah. Right. Okay. So I'll just bring this up. So I go back to Zoom, share, and it's this guy. Yeah. So I hope you're all seeing that.
Mm-hmm.
Yeah, so these are quite remarkable. Yeah, so it seems to be very consistent as they go down. They're all 3x3 convolutional networks as you go down the chain. So,
David, I have a couple of basic questions.
yes, sir.
What I have understood is that essentially, you are bypassing certain layers. Is that what we are doing?
bypassing is the wrong way of thinking about it. The term that's used is feed forward. So you're taking the activations from one layer and you're making them available untouched at a later layer.
Okay.
My intuition around this is that if you have just a set of random numbers at each layer to start with, then you essentially have to converge each layer separately. And that's fine if you've only got a few layers and you have features that are causing the activations to move in good directions quickly. But as you get into very, very deep networks, those activations will become indistinguishable from noise in a sense, and it just won't converge. By essentially having a feed-forward network, by making data that's available earlier in the chain to things later in the chain, you're giving them a much stronger indication of where the solution lies, and then they can make small changes at these higher layers to refine the solution.
So I have two problems with that theory. Maybe I'm not understanding it. First of all, at every layer we also have a bias factor, which is supposed to take care of the noise. So number one is, how does that impact? And the second more fundamental query that I have is, we have been told that in convolutional neural networks, the lower layers capture the basic features, and as you start moving through the network, you will have higher and higher order features which are getting captured. So are we saying that this theory is not applicable in the case of ResNet? Or am I not getting it correct?
You are correct, but so if you think about it from a human perspective, you get insights and then you get insights, but after you have your insights on your insights and your insights, it all becomes very vague very quickly, and it's not at all clear at these very, very high levels of abstraction what it is that how that abstraction can be represented crisply and clearly, and that's how I see it in my mind. And so you end up, what's the word they use, hallucinating. You end up hallucinating these high level features that just aren't there because you're so deep in the network and the features are so nebulous and indistinct that you really can't converge on them. So that's one intuition. In terms of the math, I'm not exactly sure. Kai, perhaps you can chime in here and
Yeah, well, I think what you want to have is a very flexible network, so a lot of parameters to capture a lot of information. So the more parameters you have in the network, the more information you can basically capture from your data. And when you have this big data sets like ImageNet, there's a lot of things you can capture with the weights. And when you do that with BGG type networks, for example, you get this problem with the vanishing gradients, and because of numerical instabilities, that's what I understood. And this is just a way to kind of make the network as deep as you think it's probably useful. And then if it's not, if you don't need it, it's not a problem. That's what I understood.
So yeah, sorry, go ahead. Please go ahead.
No, I just have one question. So if you want to discuss this further, just you can start first.
No. So are we saying that, that let's say I have 150 layers and, I decide that, okay, certain intermediate layers are irrelevant. That is where the need for residual comes in.
I don't know if they're irrelevant. I don't think that's the way to think about it. If you think about, so the way they describe it is you have y equals h of x, where h is a function of a function of a function of a function. All they're saying is that you can express exactly that same thing with y equals f of x plus x.
So see, when we say y of y is equal to f of x plus x, that plus x actually is the bias, because you see at every layer, in addition to the weights which are coming in from the from the lower layers, you also have an independent bias variable which is there. So I think what I'll do is probably I'll read the paper and then probably I'll because I think that makes more sense to read the paper first.
As I say, that the paper is very approachable. It's not at all like
Charles, just one more question. Would it be correct to say that this identity matrix layer is just a dummy layer that is in place for putting the value yeah, you said bypass is not the correct word, but it's a dummy layer that passes through the values, right?
It's a feed forward layer. So yeah, so if you think about many layers of glass all stacked together, and if they're all perfectly clear, they have no effect on the light that's passing through them. But if there's a very subtle cloudy surface texture on some of the pieces of glass, it will affect. That residual, that pond scum on the surfaces of the glass will affect what you see.
Yeah, but it's a constant feed forward layer. It's not changed during any training process. It's always this identity matrix that passes through.
Always the identity matrix. Yeah. You're just taking activations from a layer and you're just adding them to a later layer. Like it's not magical. It's literally a plus. Just to try and keep this.
So it's kind of a dummy layer to extract the information, pass it through, and put it into the feed forward part of another layer.
Yeah.
Yeah. Okay.
And as they say, I mean, it's an intuition that they gained and they tried it, and boy, did it work well. So this is, there is a pragmatic aspect to this which can't be kind of understated. And if somebody else has another intuition and comes up with something else, they'll probably, you know, have another great leap forward. So
yeah.
All right. No, just an observation. You know, our cats and dogs. First exercise was based on, I think, ResNet. So we'll have to check it out. Yeah, we'll have to read it once again to check it out. Yeah.
So just a simple point though. These networks were designed to solve very, very hard problems where you have millions of images and thousands of categories. All right. So this is not just better for everything always. I'm not suggesting that. I don't think they suggest that. If we're winning these competitions where you have 1,000 classifications and you need these higher order features in order to differentiate the difference between one species of dog and another, then this is an appropriate tool for your purposes. But that's where it came from. It came from the need to try and do better in ImageNet and in, you know, CFAR and COCO. It's not kind of some magical thing that's always better everywhere. I don't think they make that claim, at least. I don't know, but I'm just saying that they don't make that claim either. So.
Okay.
Do they talk about the, I don't see a chart in here of like training time relative to BGG. There are a lot of charts comparing accuracy to BGG and others.
I have seen that elsewhere. I'm not exactly sure. I'm just scrolling down to the end here.
It should
no, I have seen that. So if you look at the I work extensively with the COCO data set, which is related to object recognition. I don't know if anyone's even looked at it, but essentially the COCO data set, I can show you. The COCO data set looks like this. 1 moment, please. I have too many pages open. I can't spot it very easily. I can just show you this in this paper here. So I don't know what you're seeing right now. Let me just quickly share this. This one. So this is a paper on a different thing called an RNN. But essentially what happens is that you have a large image with objects within it. And when we did dogs and cats, as Jeremy pointed out, he said, this image is great because it's mostly a cat or a dog. Okay. What the COCO data set does is it challenges the algorithms to try and find multiple objects in a single image. This is very, very challenging. So essentially, there's this extremely complex stack of layers that identify candidate bounding boxes where objects might be, and then there's something that essentially tries to find a better bounding box. And then once you've got a good bounding box, then you can chop that thing out and hand it to a conventional a classifier, and all these various different things. So in these very, very complicated situations, you need to have very deep networks that can essentially have these very high order feature determinations in order for these to work well. So I'm happy to talk more about this if you're interested. I can go into the whole object recognition stack. It's an amazing piece of work.
Maybe for next time. We're coming up at
if there's
the
interest. Yeah,
top of the hour here.
Yeah, sure.
Yeah,
maybe
thanks,
add that to Kai's survey / solicitation for some of these mini presentations.
Sure. I'm happy to, only if there's interest though. The imaging stuff tends to drift away from machine learning and a lot more into image specific stuff. So like the first three layers aren't even neural networks, but if people are curious, I'm happy to come up.
I think we'll come back to CNN architectures in lesson 7. So
lesson
maybe
7.
Yeah, so maybe we can do it then.
Sure.
In 2 weeks, yeah.
Yeah.
Cool. Thank you, David.
No problem.
Hey, Kai, I have a sorry, this is just totally between me and Kai, but I want to use your Dockers, and I'm gonna, if I have questions, I guess I'll just send it to you through Slack, if you don't mind.
Yeah, sure.
Okay, thank you. That's all.
Just on that note, I set up a new machine with your latest README, and it worked perfectly. So, hi.
Oh yeah, okay. Yeah.
I'm just saying it worked perfectly. Like I literally just followed the instructions step by step and on a new machine.
Yeah, great.
Yeah, so no issues there.
Yeah.
Awesome. You had something, Mahesh?
No, I just wanted to thank Kai. I think he's the guru in the group, so that's yeah.
A bunch of gurus.
You're welcome.
From my perspective.
Yeah.
But yeah, thank you all.
Thank you.
Awesome. So next time is RNNs.
Okay.
Excellent.
All right. Catch everyone next week.
Okay. Have a great.
Bye. Thank you.
Have a great weekend, all of you. Take care.
You too. Bye.
Take care, guys. Bye.
Bye.
Bye.